Hi. So in this video, we're going to look into the notion of cut generation within MIP solvers. So cut generation is a process that is familiar to us, really. It's the idea of reusing perhaps a cutting plane approach to solve the MIP. The main difference is that in the context of MIP solver, the cut generation is only one part of the whole story. Meaning that combined with the process of branching and bounding, we also have a process of generating cuts, which leads to the name of branch and cut, as is known. The method employed by these solvers is generally known. And the main idea of combining branch and bound with cutting planes method is because you're trying, to some extent, to strengthen the formulation before you apply branch and bound. So when we looked at what it means to have an ideal formulation for an MIP and what there's an idea to have a better formulation to an MIP, we saw that it amounted to having formulations that were tighter. The tighter, the better. And cutting planes, they do exactly that with our formulation. They make it an iteratively tighter. All right. You have to be careful the way you deal with your cuts, because it might be so that you're generating too many of them and you quickly make your problem challenge to solve with too many constraints, leading with large matrices to manipulate. So one technological advancement that is very important in this context is this notion of cut pool, which are cuts that are considered implicitly. Basically, very simply put, a cut pool works like so. You don't have the constraints explicitly considered in your, say, simplex tableau or in your B matrices. But once you find a basis, and you want to check whether that is optimal, you refer to the cut pool and check whether that solution satisfies all the cuts in your cut pool. Because if it doesn't, then you have to retrieve that constraint that is being violated and bring it implicitly to your basis, or to a B matrix. We know how we can do that efficiently with simplex, with dual simplex. But one important thing to bear in mind is that there is some sort of overhead, or trade-off even, in considering cuts to live in the cut pool, which involves this sort of testing and re-including, or by having the cuts from the get-go in the formulation, you don't have to do these extra steps. So this has to be sort of cleverly managed in order to be efficient, but it is widely used by the solvers to make more efficient the process of considering simultaneously so many cuts. Most of them are, the solvers allow you to define user-defined cuts. So other than a predefined selection of cuts that each solver has available, you can almost quite often define your own cuts. So if you happen to know a specific inequality that is valid in your problem, you can include that in your branch and bound process. Very problem specific, of course, but if you know some, you can use them. And the cut generation is perhaps one of the most, I wouldn't say perhaps, but it's certainly one of the most researched areas in MIP solver technology development. There have been emerging quite interesting ideas where you combine the generation of cuts with information that is learned during the solution problem, or that is learned by looking at several instances of a given problem. And whenever you say learning in this context, is obviously machine learning becomes something to have the potential to be beneficial, and here is the case. So cut development, the selection of cuts that is available for the solver is one of the main things that differentiate commercial open source solvers. The collection of cut types they offer, and also it's something that is typically changing from one version to the other. Not typically, but sometimes you see when a new version of a solver comes out, one of the main differences is either a new family of cuts or a different way or a more efficient way to generate cuts for a given family. So it's very important in the context of MIP. So here are some examples of cuts we actually already know. You might have seen when we're using, for example, CBC. CBC sometimes say that it generated a few Gomery cuts, and they are exactly the fractional cuts. Sometimes they're called Gomery fractional cuts. Those that we're seeing when we talked about cutting planes. So you already knew some of them from when we looked about cutting planes. Another that you're familiar with is the Shvatal-Gomery cuts. Sometimes these get called fractional cuts, and these get called just Gomery cuts. There's a bit of a confusing nomenclature way to refer to these, but these are Shvatal-Gomery cuts and were developed a few years later than the original fractional cuts. And also, on top of Shvatal-Gomery procedure, depending on the sort of method that you use to define it, the weights U that you use to combine the constraints, that gives you a specific family of cuts. So I'm putting here two examples that I know it's available in many solvers. I'm not going to discuss how they are, but you might see references to things like zero-half cuts. And zero-half cuts are basically cuts that are generating setting these used to be either a number between 0 and 1/2, hence the name. There is also mod K cuts. So mod K cuts is a bit more complicated, but basically you're setting a constant, and then what you're doing, you're getting fractional values of that. So I don't know, you can set K to 7, and then you 1/7, 2/7, 3/7, 4/7, and use those as weights. These are a bit more complicated, but you will see quite often mod K cuts as well. Quick Google, you'll see how you can find quite a lot of material on how these are generated. It's not that complicated, but I just want to mention to see that with the knowledge you have now, you are just a short step from understanding now where these things come from. And there are quite a few other more. So I recommend, for the sake of curiosity and scientific curiosity, whenever you see the name of a cut, it's the first time you see. Now, go about and Google a little bit, and soon enough you're going to see that it's likely to be a combination of a Shvatal-Gomery procedure with the definition of weights, or sometimes it's just defined heuristically, like the ones we've seen before. That doesn't necessarily go through Shvatal-Gomery, but goes through looking at specific structure that the problem might have that can be exploited to generate cuts. So just to finalize, one thing to have in mind is that just generating cuts at random is not sufficient. You also have to be careful something related to cut management. When to select, when to generate, when to select, and when to discard cuts. So you have to take into account, for example, that as you adding cuts to your LP, it costs to resolve it. You're making your structures larger and larger. So there must be some management associated with that. Also, more cuts will imply larger models because you have more constraints at the end of the day. To obtain the cut, sometimes you might have to solve a separation problem. And you can think of a separation problem simply as this process of trying to find and execute an heuristic or execute a procedure that can give you the cut. Lifted cover inequalities, for example, require an heuristic procedure that is almost solving a minimization problem. So it might be so that you have to do some work to generate a cut, which might involve solving a subproblem. And you also have to take into account, how do you select cuts to consider? If you can generate a collection of them, you have to select which you think would be the best. And there are some criteria that can be used for that. One of them, for example, is this notion of numerical stability. You don't want to generate cuts that have, too small or too large coefficients, because they might introduce numerical instability in your problem. So if your coefficients are, very small or very large, you tend to discard the cuts because they might cause trouble in terms of numerics. You can use a measurement of how deep your cut is getting into the LP region. So basically, and you can estimate that by thinking of the idea of, getting this point, which is the solution of the LP, and then just measuring a distance to the cut you just introduced, which could be, for example, this distance d. And the bigger the distance d, the deeper you're getting into the linear relaxation, and hopefully that's a good thing. Typically that's a good thing. So if you're trying to decide whether to introduce, say, D1 or I don't know, D2, instead of adding both, you can select D1 and criteria like so. There is also this notion of orthogonality. There's a arm missing there, and another one here. So you look. You want a new cut to be sort of pairwise orthogonal with the cuts you already have, and most importantly, as orthogonal as it can be with the objective function, because it basically means that you are. So again, this is our feasible region, and suppose you have this is the vector C we're maximizing, just to make things easier. So this will be, I don't know, our XLP. So you want when you add a new cut, you don't want your cuts to kind of, cut things in this direction. It is nicer if it goes and cut it like that, right? And most importantly, if it can be somehow as perpendicular as possible to this, the better, because that sort of giving you a bit more chance to find cuts to cutting parts that are really relevant in terms of your solution search. Because if you're cutting things in that direction, say, it's not really helpful because you're moving this way. So even though you're discarding some part of this feasible region, it's not as effective as having something that cuts like that. So this notion of orthogonality with other cuts that are already there and with the objective function can also be used to kind of infer whether, give a score to the cut. Of course, these are, sort of criteria that have to be taken into account in combination. And we talked about cut pools before, but I'm just bringing it here. Cut pools is a way to manage what cuts are being considered. They allow you to define these. They are called lazy cuts, and lazy cuts are basically cuts that are considered in a cut setting. So your cut pool might have so the cut pool involves lazy cuts like we described before, but it might also involve user cuts, and user cuts, they not necessarily need to be checked, but they can be generated on the fly. But lazy cuts are those that are in the cut pool like I described before, meaning that they are checked against violation once you find a solution to declare that the solution is truly feasible. So the lazy cut means that you can consider the cut, but without having to manipulate it in the matrix. Okay. So yeah, I think that's all I wanted to say about cuts. So in the next video, we'll talk about variable and node selection, and then we'll talk about primal heuristics. So see you in the next video.